So far in this unit, we have learned a lot of new things, but perhaps one of the weirdest of all is that there is a particle called a neutrino. It has no protons, it has no mass at all, almost, very, very small mass, and it has no electric charge, and to make matters worse, it doesn't really interact very often with things, so they're incredibly hard to detect. In fact, right now, there are around 100 trillion neutrinos passing through your body every second. So they are so non-interactive that they pass clear through your body without interacting with any of your matter. How do we know they're here? It comes down to momentum. Momentum is conserved during a collision when there is no friction. This is what we learned a while back, and the equation that really expresses this is shown below. If we put this scenario, consider the scenario where there's a person holding a snowball, let's pretend that she's on frictionless ice skates on a frictionless surface. When she throws the snowball forward, the ball feels a force forward, and according to Newton's third law, her hand feels a force that is equal, but in the opposite direction. Because of that, because the net force on both objects is the same, we could multiply, just opposite directions, we could multiply both sides by the time that they interact. F net times delta t is the net impulse. And impulse, net impulse, we know is equal to change in momentum. So they have the exact same change in momentum, they're just opposite in direction. And if you add delta PA to both sides, we get 0 equals delta P total A plus B. So there is no change in momentum from initial to final. Okay, if we look at the picture on the left, what's the total momentum? 0 if they start at rest. There's an interaction that occurs. And what's the total momentum at the end? 0. How do we know? Well, the ball's positive momentum must cancel out exactly her negative momentum. They add to 0. That's called recoil. She recoils during this collision. And of course, that just means she moves backwards in the opposite direction. But the same thing happens in radioactive decay. Total momentum is conserved. The parent nucleus recoils. And the final momentum of the two particles at the end has to add to the total momentum of the parent. Okay then, let's see this in action. You've got a big nucleus here that's at rest, or maybe you take the frame of reference of the nucleus so that it's at rest. And then during this decay, you eject a really high-speed alpha particle, which is just a helium nucleus. You could write it like this or like this. And what happens? The daughter recoils, moves back in the opposite direction. It is important to note, however, most of the Ke that's produced in this collision, this is, by the way, a super elastic scenario. Super, because the objects start together, they end apart. Most of the kinetic energy that's created is given to that small alpha particle. The smaller mass receives most of the kinetic energy, but they have the exact same momentum, just opposite directions. We can also apply this and visualize this with gamma decay. The gamma is emitted off this way, and as a result, the daughter recoils. And you expect me now to say the same is true for beta decay. And yes, it is, but it didn't look like it. Here was the problem. They saw momentum conserved in alpha decays. They saw momentum conserved in gamma decays. But when we looked at beta decay, the daughter kicked off this way, and the beta particle kicked off in a direction that didn't make any sense. It was true for negative beta decays as well. Momentum appeared not to be conserved. The only way this type of a picture makes sense is if there is another particle that we can't see which is moving in the opposite direction, kind of off this way. Likewise, the same new particle would explain how momentum is still conserved in these negative beta decays. That was our first evidence of the neutrino and the antineutrino. We could make a similar argument for energy. It's worth checking out. Go look it up. Energy was also appearing not to be conserved during these decays unless you invented a new particle. So that was our experimental evidence for the neutrino. That's where it came from. Try this exercise. Try this exercise and see if you can outline the experimental evidence that the neutrino must exist. This was our first evidence, but much more evidence has been produced since then. Okay, next up, we're going to flip ahead in our notes to page 13, and we're going to see how to determine half-life using a graph. On this graph, the x-axis is time. The y-axis is the number of radioactive nuclei remaining. So when no time has passed, no nuclei have decayed. How much do we start with? Well, this is counting up by 1 times 10 to the 25. So right here we start with 32 times 10 to the 25 radioactive nuclei. As time passes, some of them decay, so the number that remain decreases. They transmute into a new substance. And okay, so how long does it take to drop to 1/2 of our starting amount? Well, half of 32 is 16. So let's trace over. Here we are. Took 6 days to drop in half. Let's drop in half again, down to 8. We go over, trace down. That's 12 days. Okay, what's the half-life? You can figure it out. 6 days. And if we let 6 more days go to 18, you would see it down to 4. Half of 8 is 4. So that's how long it would take to get down to 4 if we were to extrapolate out. Okay, so take a moment. We could answer this question. How long does it take till 25% of the sample remains? Well, if you start with 100, cut it in half, that's 50. Start with 50 now, cut it in half again, that's 25. 2 half-lives is 6 plus 6, or 12 days. But you could get that from the graph as well. Okay, a second sample of a different isotope has the same number of nuclei, but half the half-life. So we start at the same spot, but now you drop to 16, not in 6 days, but in 3 days. So there's a data point right here. Then you drop down to 8, not in 6 more days, but in 3 days after that. So right here, whoops, let me mark it like this, and let me mark that data point. So, you've dropped in half again, it took 3 more days. You drop in half again to 4, that takes 3 more days, 9. And where's that data point going to be? Right here. And now go down to 2, and that takes 12 days. And we could sketch a graph. It's going to look something like this. Oops, my touch is a little bit off right now, so it looks a little more jittery than normal. And the graph continues. And I think we're supposed to mark that with Y. There it is. Finally, we have a third sample, isotope X. It initially has 16 times 10 to the 25 nuclei. Draw the curve, label it Z. Well, what's the half-life? Oh, it's the same as initially. 6 days, because it's the same substance. Ah, that's tricky. So we know the half-life is still 6 days because it's the same nucleus. Maybe it's radium or something, although not radium because radium's half-life is not 6. But you get the idea. Same half-life, but now, for curve Z, we start here. So after 6 days, we cut in half. We're here at 8. After 6 more days, we're at 12, and we've dropped to 4. And so that graph is going to look something like this. The red dots. Connect the red dots. Let me try again. Like this, perhaps. and that one I label Z. So that's how we solve problems involving half-life and graphs.